Hello, everyone again. Good morning to Eric and Glenn and Ben in the United States and the audience, the rest of the audience in the States. Here it is the afternoon. Two comments. First, if you don't mind, please have your cameras open. It's nicer for the speaker and for us to see each other. Second, since the audience has a reasonable number of people, and in accordance with the preferences of Glenn, you can just unmute yourself when you want to ask a question and go ahead and directly make a question to Glenn. When you're not asking a question, please keep yourself muted to avoid background noise. Glenn, thanks a lot for being with us, for putting the effort into this, time and effort into this. The floor is yours.
I have sorry, not a question for Glenn, for you. Are the videos of the talks available? Or it's only streamed online and that's it?
We are being recorded, so it should be available.
But can I get the link? Yes, because I missed some of the talk yesterday and I wanted to see it and I have no idea how to get to it. Okay, so ask the people at YAS to send us the link.
We'll do that.
Okay, thanks.
It is a tradition of the summer school to post the lectures online and also the slides. So Glenn and Ben, if you are happy with that, we'll do that with your lectures.
Actually, Glenn has already sent his slides and they're already posted.
Oh, okay. Head of the curve.
Yeah.
Okay. Well then, thank you everyone for inviting me. Happy to be giving this talk. So today I'm going to be talking about epidemiological models, obviously motivated by COVID and helping to understand what, I think I said two roles. One is sort of understand what's going on with COVID, and the other is sort of give background to students and others who are thinking of doing economic analyses, discussing sort of the COVID pandemic as something they're trying to get at. Okay, so let me start with, I don't know how familiar this is going to be, but let me just start with the benchmark model in epidemiology that's used often for discussing epidemics, and that's the SIR model. So this is it comes from a paper from 1927. It's still, though, a very elegant way to bring out intuitions. I think, there have been a number of economists take it even more seriously than they should, but let me go through the model. So in this model, you have a unit mass of agents. Every agent is in one of three states: susceptible, infectious, or recovered. And what we keep track of is the population fractions. S of t is the fraction of people who are currently susceptible at time t. I of t is the fraction who are currently infectious. R of t is the number who are recovered and no longer infectious. So, S plus I plus R equals 1. So really R is just redundant. We really shouldn't have it there, but that's how the model is usually done. Motivation of this model is you imagine that when someone gets infected, they remain infectious for an exponential period of time with mean 1 over gamma. So they recover at Poisson rate gamma and are infectious until that recovery occurs. That's done not because it's a good model of infection, but just because it's the most tractable model of recovery that makes the algebra work out well. And then the second, you assume that people are moving around and bouncing into each other, and they have these random interactions with others that would transmit the disease if the person on the transmitting end isn't currently infectious and the person on the receiving end of the interaction is susceptible. And so what we assume is that infectious agents are moving around, they bounce into other people and have these dangerous interactions with probability R0 gamma dt in each dt time period, which means that over the 1 over gamma course of their infection, they're going to infect R0 others if they're bumping into susceptible people. And so that leads to the top line here. I dot is S of t, I of t, R0 gamma, because with probability R0 gamma dt, you bump into somebody. If you're infectious, they're susceptible, then you transmit the disease. So those are the basic dynamics of the system. So it's just a three-dimensional system of differential equations.
Can I ask a quick question?
Yes.
I don't know if you can hear me well. Are we assuming in this model that the recovered are immune, at least partially?
Yeah, so in this model, the sort of, S dot is minus, so everyone it says that when everyone becomes infected, they are no longer susceptible, they're no longer susceptible permanently. There's no flow from R back into S. So, and typically, obviously, epidemiologists have worked out many other models. There's an SIR-S where you go from recovery back to susceptible over time. Simplest version, recovery is permanent and 100% protected. Okay, so, basic properties of this model. One is, R naught is a critical parameter. If R naught is less than 1, then the infection-free state is locally stable. This is a disease that will not spread. We don't have to worry about it other than sort of small random growth. When R naught's greater than 1, then the sort of steady state where no one is infected is unstable. One person gets infected, this thing spreads through the population and takes off explosively. The growth rate in the model, so I define the growth rate to be the derivative of the log of the rate infected. So that's just the change in IT over IT. So the growth rate is gamma R naught S of T minus gamma. The minus gamma comes from the recoveries, and then the gamma R naught S of T comes from the infections. And if you actually ask, practically, where do these R naught parameters come from when people are describing epidemics? You might think, well, can you early in an epidemic take a particular person who has a disease, find everyone they've infected, count them up, that gives you R naught? That's not the way it's done. The reason is because just, contact tracing is always very incomplete. So what you do is typically people estimate gamma times R naught from the growth rate of new hospitalizations. And so you use that as an estimate of gamma times R naught. And then the gamma, the recovery from the disease, that you can get with contact tracing data, because you can, for each person who's been infected, you figure out who did they get it from, how many days into that person's infection were they. That lets you estimate the distribution of recovery times. You divide your gamma R naught estimate by your gamma estimate. That's where you get R naught in practice. Okay. If you have a new variant, like we have the Delta variant comes to a new country, estimating R naught of a new variant is harder because the initial growth rate is not gamma R naught, it's gamma R naught S of T. If it's a new variant, some of the people are already not susceptible to the variant. And if it's a new variant, you don't know what fraction of people who had gotten the previous disease or have been vaccinated are susceptible to the new variant. And so then estimating the R naught of a new variant is harder. And you've got to sort of figure out some way to decompose the R naught part of it and the S of naught part of it. Crucial concept here is the herd immunity threshold. So let S upper bar, I'm going to define as the herd immunity threshold, is such that S00 is a stable steady state if S is less than S upper bar, and S00 is an unstable steady state if S is greater than S upper bar. So this is the crucial fraction of the population that can be susceptible to have it spread or not spread if there's a very small infection. And this concept is incredibly important. When I know early in COVID, many epidemiologists had this very, very fatalistic attitude that there's really not much you can do. And this comes from a long history that you can do all kinds of things like temporary reduced activity, get everyone to wear masks, trace the people who get test positive, enforce quarantines on them. But anytime that those things start to get relaxed, the infection is just going to stop spreading again. Unless you can get it to like absolute zero, as some countries like New Zealand have tried, anytime you get away from zero, the thing is just going to spread again unless you put the restrictions back on, and nothing stops that until you get S. Nothing stops that until you get S below S upper bar. So, if you take the classic SIR model, S upper bar is 1 over R naught. So if you take the original Wuhan strain, R naught might be 2.3. This would be about 0.44, which would say it's really hard to do anything that gets less than 56% of your population infected. The alpha variant that came up in England, R naught's like 3.5, people think. Therefore, S upper bar would be 0.29, so you need 71% to become somehow immune. Delta variant, R naught maybe 5.5. I think that one is harder to say because the Delta variant only arose in populations where there's already the confounding of who is immune to it. But that would give you S upper bar is 0.18, so you need 82% to be immune somehow. Obviously one way to get immunity is to have people be infected. The more desirable way is to get people vaccinated. You can think of vaccinations as reducing S of T, but let's suppose you have a vaccine that's 90% effective, which is a remarkably good vaccine, which we seem to have. SIR suggests that you need to vaccinate or infect 80% of the population with something that's 90% effective in order to reach herd immunity against the alpha variant. So, in some ways, the SIR model seems overly pessimistic in that, no one has managed to vaccinate 80% of their population yet, and yet we still seem to have places where we hope at least that we've reached herd immunity against some of the common variants. Okay. The S upper bar is in some sense, that's the sort of inevitable limit that you can't stop this thing until you have fewer than S upper bar who are still susceptible. But if you look at an SIR model, it says that you're going to get many more people than that infected. That's actually a best case scenario, not a worst case scenario. So, the SIR model, if you calibrate to COVID-19 like R is 2.3, it predicts that an uncontrolled epidemic is just going to explode, reach herd immunity very quickly within a month or two. Many, many people are infectious on the day in which herd immunity is reached, 10 to 15%. And when herd immunity is reached at the peak of the epidemic, and at the peak of an epidemic, that looks fairly symmetric. And so what happens is, number of cases, when you reach herd immunity, the number of new cases per day starts to go down, but it's already so high and it goes down at a limited rate that you end up with many more people infected. How many people do you end up with infected? Well, let me write S of infinity for the fraction of people who escape infection. That means eventually 1 minus S of infinity people are going to be infected. Each one is going to have R naught of these dangerous interactions with somebody else. Therefore, if you think about it from an ex ante perspective, if you're someone who's entering this population, how many times are you going to get hit? Well, it's going to be Poisson with mean 1 minus S of infinity R naught. And so what's the chances that you escape infection? Well, it's just the chances that you get 0 in a Poisson random variable with mean 1 minus S of infinity R naught, which means that S of infinity equals e to the minus 1 minus S of infinity R naught. And so if you solve that equation implicitly, what you find is the difference is very large. So for instance, with R naught is 2.3, you get S upper bar is 0.44, S of infinity is just 0.14. So while you could have 44% escape infection, theoretically, if the thing just goes out uncontrolled, you're going to end up with only 14% escaping infection. And if you look at there's a number of economics papers have been written sort of talking about the trade-off between reducing activity, which both reduces infections and economic activity, and controlling the disease. And what those papers are often doing is those policies that are optimal are the ones that are designed to reduce overshooting. It's often that if they don't have a vaccine and they're coming soon, there's nothing you can do to stop reaching herd immunity, but you can stop all of this overshooting. And so then the policies are designed to stop this overshooting. Sometimes there's also an effect of they're designed to sort of lower the peak so that if you assume that hospitals become less effective when they're over capacity, you get more deaths, that's a second factor. But typically the economics papers are being written, they're about overshooting and stopping this excess number of cases.
Could you maybe define overshooting?
Yeah, so overshooting is the number of people who are eventually infected beyond the herd immunity threshold. So if you have you can reach herd immunity when you have 56% infected, 44% susceptible. But if you let the epidemic proceed uncontrolled, it goes so fast that you end up with 86% infected. And so 86% minus 56% is the 30% overshooting. And those were the cases that didn't need to happen if you don't have a vaccine. Okay, so if you look at what epidemiologists do, so many economists are using these sort of SIR models. Epidemiologists have sort of, this is a 1927 paper, people who moved past it in 1929, many, decades and decades and decades of variants of SIR that people think are better than the SIR. A lot of these things are very, very common in epidemiology. One is, adding a state for people who are exposed but not yet infectious. That's very important for COVID-19. People become infectious a few days after they're infected. That time when they're not yet infectious is a crucial opportunity to stop the disease. Adding in quarantine states, and sometimes the way contact tracing works is you take people who are exposed but not yet infectious, you stick them in a quarantine state, you keep them there until they're no longer infectious, and that stops the spread of the disease. Making recovery time distributions more flexible. This exponential thing is a nice mathematical formula to give us things that are easily tractable. In practice, that's not what recovery time distributions look like. Mapping that correctly is important. Particularly if you're sort of a policymaker at a university, at MIT, we had a testing regime where we were testing everybody twice a week, and then we had a quarantine protocol for gathering contacts of people. If you're thinking about policies like that and how effective they will be, whether they will control the epidemic, getting all these other parts of it right, the exposed but not infectious, the time distributions, those are really important. I think they're probably not so important to model. Like if you actually just sort of simulate, well, what's the course of an uncontrolled epidemic in an SEIR model with whatever, you'll find that the time path looks almost like the SIR model. So they're not really important. They're important for the micro details of how effective are your contact tracing and control processes. They're not really important for the ultimate effect of an uncontrolled epidemic. But then two other concerns that I think I want to talk about, spend most of my time today on things that are important to overall epidemic trajectories are, one, endogenous behavior. That SIR model, it treats R naught as a primitive, the number of people you bump into. In practice, there's just no way that SIR model could be correct. The SIR model, you have a day when 13% of the entire population is currently infectious. No one will leave their house on that day. People will stay in their house, they will wear N95 masks and be like, wow, we have 2 weeks when like 1 out of every 7 people I meet is infectious, I will just stay home. And so there's no way that you can get epidemics going as fast as those models predict.
Can I ask a question?
And then, was there a question?
Yeah, sorry, I didn't want to interrupt.
No, go ahead.
So it seems like the SIR model is very similar to search and matching models. And I was wondering, what's your thoughts on using one versus the other? And when talking about endogenous behavior, there is the early Pissaridis and others paper that actually switches from the SIR to search and matching to endogenous behavior. So what?
Yeah, no. So I 100% agree that we should be using models with endogenous behavior rather than the SIR model with R naught fixed. I mean, I think in some sense the R naught fixed is a very like some of the intuitions are going to be very general, like the herd immunity problem. Whatever search endogenous thing you have, as soon as people start endogenously interacting more, they're going to run into the same thing. The thing's going to take off. You're still going to reach S upper bar eventually. So I think this model is a simple way to bring out some intuitions, but yes, I think we should 100% be using, I don't know if we should exactly be porting over the models we already have for people doing search and things like that, but variants of them we should definitely be using rather than SIR. Okay, and then the second thing I was going to say is, heterogeneity. In practice, contact rates vary dramatically across people. People who ride public transportation, people who go to bars, people who work in, meat packing plants or other jobs that have close contact with people, people who live in sort of dense urban neighborhoods that have overcrowded homes with many people sharing rooms. These people are going to have many more contacts than others. it's also often the case that those people with many contacts, many of the contacts they have are with other people who have lots of contacts. And then other people, on contrast, stay home and interact very little. And so there's a lot of heterogeneity in the population. I think that's very important to account for. When we start working with models with vaccines, you really then also have to think of it. Sometimes people who are vaccinated are people who now have much lower contact rates than others, because contact means interact with someone in a way that will spread the disease to them. And so when you want to start thinking about models where people are vaccinated, then you also have to start going to models with heterogeneity rather than this sort of simple one-dimensional SIR model. Okay. I'm going to start today with sort of heterogeneity and then talk about the endogeneity towards the end of the talk. Okay, so first, heterogeneity. So I'm going to, again, this is now picking up, I've jumped 60 plus years or 70 years or so in epidemiology to sort of what were the classic models of SIR models with heterogeneity in the 1980s or 1990s. So let's take an SIR variant and suppose you now have n groups. Suppose the activity levels differ across the group. So now we have R01 is the activity level in group 1 up to R0n is the activity level in group n. Assume that members of group I have contacts with probability R0I times gamma times dt. So I guess this will also be familiar to people who start thinking about like models of job search of people bumping into each other. So we specify this overall contact rate for people in group I, and then we also have to specify who it is that they bump into, and we have to do this in a mutually consistent way so that people in group I bump into people in group J with the same frequency with people in group J are bumped into. Simplest model of this is the pure uniform random matching model in a population. So then a formula that works out is person in group I's contacts are in group J with probability R0J divided by the sum over all K of R0K. So it's basically everybody is interacting in the population, just some people are sort of out there more often than others. Whenever you're out in the population, you're like equally likely to bump into anyone who's out there. And so that creates this sort of, you bump into people in proportion to their activity level. Okay. What would this do to the SIR model? Well, basically it's just changing this sort of new infection rate. And so the new infections in population I are SI of T, the number of people in population I who are currently infectious, times sum across all J of beta IJ, IJ of T. So basically people in population I get infected if they are susceptible and they get bumped into by someone in population J, and that person in population J is themselves infectious. So the beta IJ coefficient there is just gamma R0I, my activity, R0J over sum of R0K, the fraction of those people who are going to be from group J. So it's just the fraction of my interactions, which are with someone from group J, multiplied by the probability that person from group J is infectious. Okay, so it's the simplest uniform random matching model you can make up. How do you analyze a model like this? Well, now the state variable, instead of being a constant I of T, the key state variable in infectious people, it's a vector, I1 of T, I2 of T, IN of T. But as we typically do, if you're trying to analyze a differential equation and understand whether it's stable in a neighborhood of a steady state, you linearize a differential equation. And so you can linearize this differential equation in a neighborhood of the I equals 0 state, I equals 0 being a vector of zeros. And you get in a neighborhood of that 0 vector, it's going to be approximately I dot of T is going to be some matrix A times I of T. And when is a differential equation like that stable? It's stable if that matrix has all of its eigenvalues less than 1. And so, you can, in this sort of model, the model's been nicely specifies that we can actually look at that matrix A that applies to it. The matrix A just comes from, it's a matrix with those betas in it. We write down the matrix, we find the largest eigenvalue, and it turns out you can get nice, easy analytic expressions. They're actually fairly obvious. So the case distribution, what is the largest eigenvector? Well, if you start with a very small infection, it's going to grow in proportion to activity levels. So the people in the highly active group are going to get more cases. People in the less activity group group are going to get lower cases for that reason. And so the principal eigenvector is just the initial susceptibility times the activity levels, and that's the direction in which the epidemic grows. It grows in proportion to activity levels. And then once you know that, it's easy to figure out what the eigenvalue is. The eigenvalue is what I've written down here, gamma times the sum of SI naught R naught I squared over the sum of R naught I minus 1. So that's the growth rate of the epidemic in this heterogeneous model. Okay. Thing to notice, this thing initially grows exponentially. That's just like the SIR model grows exponentially. And so when you have an epidemic with heterogeneous interactions, it looks just like an epidemic with homogeneous interactions from outside looking at it. And it just grows at this exponential rate that you can estimate. And you're going to estimate that it grows at this exponential rate when we start with the S is equal to 1. It's just R naught upper bar is just going to be sum of R naught I squared over the sum of R naught I. So what does that mean?
Question, Glenn?
Yes.
I understand. I mean, you are doing this at the point I equals 0.
Yeah.
Now, it's true that we are hoping that I is not going to be too big, but still, we could talk about I being 1% of the population, and maybe things will change if you do it not at 0. Because for most of the, or it's not going to make a difference once you do the analytics, and it's essentially the same.
I think it's not going to make much. Think about it, like normally when we're talking about we're doing theory on other topics, and we're like, well, let's suppose that I is we're analyzing this thing in a neighborhood of I equals 0, and you're going, okay, what if I is 0.01? 0.01 is awfully close to 0, and 0.01, like these things are fractions of the population currently contagious, and those things have always stayed fairly small. It is true that so if you're thinking about like early growth of an epidemic, or most of the phases we've been in, these I's have been very small. In India, in the peak of their thing, the dynamics look different from this. But if you're thinking about like what's the Delta variant in Israel right now, I is 0.00001. So the I equals 0.
Now at this stage of the game, I equals 0 is very good. But at early stages, maybe not. I'm just wondering if But I agree that probably I is quite small, so it should make a big difference.
Yeah. And
we are talking theoretically. That's what I wanted to know. How much?
Yeah. And I think what goes on is like early on, people often it's early in an epidemic that people want to ask, how contagious is this new variant? What is its spread parameter going to be? And so if you use the early data to estimate its spread parameter, this is what you're going to be estimating. You're going to be estimating sum of R naught I squared over sum of R naught I. Two ways to see what that thing is. One rewriting is I just pull out one of the R naught I's and view it this first expression, sum over I, R naught I over the sum times R naught I. That's saying this is a weighted average. So when you're just estimating the weighted average of the group by group contagiousness or activity levels, where you're putting more weight on the highly active groups. Another way to rewrite this expression is to note that it's equal to the expectation of R naught I plus the variance of R naught I over the expectation of R naught I. And so this goes up. So in some sense, more heterogeneity with a fixed average infection probability makes the thing grow faster. And so when when people are giving you an early estimate of what is R naught, it's in a heterogeneous world, they're always estimating this weighted average. They're not estimating the arithmetic mean. Obviously, that's okay, because what they're interested in is this weighted average, but it's important to keep in mind that that's what we're always seeing is these weighted average of infection rates, not arithmetic averages of infection rates. And we really emphasize the high R naught people, because you've got these R naught squareds there.
Let me ask about the previous point.
Yes.
So you said that the larger the variance, the faster it spreads. But I'm assuming that if people with high R naught I are more likely to interact with others with high R naught I, then this is no longer the case, right?
No, then this is true, and this is true even more. Actually, I'll get to that on the next slide.
All right.
Assuming that they are all connected. It's assuming they are all connected. If it's split into two populations that do not interact, that's not true.
That's right. So this population now, this is pure uniform random matching. However much like everyone goes to the market, however much you're in the market, you interact with everyone else at the market, and it's just the number of times you go to the market every day. or every week.
Yeah, the beta ij have to be positive for all ij. Yeah.
Yeah. Okay, so now generalization of that to actually get more realistic, as Nikita was asking. So, people with high R naught are naturally going to interact with others at a higher R naught. The people who go to the bars are going to meet other people who go to bars, and they're not going to bump into people who don't go to bars. People who ride the subway are going to meet other people who ride the subway. People who live in crowded, low-income neighborhoods meet other people who live in crowded, low-income neighborhoods. So now, simplest generalization of this, suppose the probability you meet people is H plus 1 minus H times R naught J over R naught K. So you can think of this matching process I've written down as just with probability H, you're matched with somebody in your population, and with probability 1 minus H, you're uniformly randomly matched like in the previous model. And so H is something that's between 0 and 1, where H equals 0 is uniform matching, H equals 1 is entirely within group matching with no cross-group boundaries at all. H is 0.99, 99% in my group, 1% random interact with the population. Okay. So what happens with this? Well, you just, I'm changing the contact probabilities, but it's just exactly the same dynamics. Change in infection is at fraction susceptible to my group times these contact rates times ij. Okay, where now the betas just look like this, but with the H times 1 plus 1 minus H times R naught J if it's in my group, and the no H if it's outside my group. Turns out that this model is also tractable, and this was also worked out in the 1990s. What happens in this model? Well, you can say a few things. First, every population, in order to have the epidemic in a herd immunity region, every population must be what's called internally stable. That is, you have to have SI naught times H times R naught I to be less than 1. Because that's the number of contacts people in group I are going to have just with other members of their group. And if the number is susceptible and the H is high enough and the R is high enough, then it's just going to explode entirely within group I, even if it's 0 in every other group. So obviously, it's an obvious statement that you can't have H R naught S too large in any group or the thing is unstable. What happens otherwise, though? Again, we just, same exercise before, we do I dot equals A times I. We now plug in these beta IJHs instead of the beta IJs in the model, and then we find the largest eigenvalue of a matrix, and we see when is that largest eigenvalue greater than 1 or less than 1. Turns out that's also a tractable calculation, and what you get is there's this critical threshold equation, which is, you remember before I could have rewritten what I had before as, I didn't write it that way, R naught I times SI naught over R naught minus 1. Well, let me write it here. So what I get is sum over I, R naught I over sum of R naught K, times, let's look at the third term, SI naught R naught I minus 1. Set H equal to 0, the middle term is just 1, and this is the same expression as before. Whether something's unstable, it's just a weighted average of SI naught R naught I minus 1, where the weighted average puts more weight on the highly active groups. Now we just get this extra term in here, 1 over 1 minus H SI naught R naught I. So this is a new reweighting, and it's a reweighting that puts more weight on the more active groups. Because this weight is larger when H SI naught R naught I is closer to 1. So the more active groups are just getting more weight. So it's simply a reweighting of the previous formula. It's a reweighting of the previous formula that puts more weight on the more closer to non-herd immunity groups. Therefore, it always makes things worse because it's putting more weight on the sort of more dangerous groups and less weight on the less dangerous groups. Okay. So the theorem is, if a disease-free equilibrium is unstable for some H, it's unstable for all larger H. So homophily always makes things worse. So if you have, homophily just makes things more unstable. Any allocation of susceptible people across groups, if it was stable with low H, with high H, it's wherever there's like that boundary level of H, and above that, it's going to be unstable. Okay. Any questions? Okay, so homophily is bad. It does give us these, again, we have these formulas. We can comment on how bad it is. Let me just sort of bring out some of the practical implications of this. And it turns out that, my first take on this is that these are very important factors and they don't often get discussed. So let's take, many people treat COVID as a homogeneous SIR model with parameter R naught bar, the one you would estimate. And suppose we think that R naught bar is 2.3, as people often use in papers. Where might that 2.3 come from? Here's one example of where 2.3 could come from. You have 5 different subpopulations. One group where the R naught is 3.5 instead of 2.3. They're just 50% more active than the quote average. Another group where it's 1.5, another group where it's 1, and then 2 other relatively inactive groups where it's 0.5. Okay, if you work out the R naught bar for that combination, I've set it up so that those things in fact do add up to 2.3. So weighted average, you put more weight on the 3.5, the weighted average is 2.3, S naught hat would be 0.44. So if you do the sort of, think of it as a homogeneous epidemic, you'll say we need 56% vaccinated to defeat this epidemic. Well, one common for these models is the heterogeneous model suggests you can get massive overestimation of the required infections or vaccinations to stop a pandemic. In the uniform model, you don't need 56% vaccinated, you actually only need 14% vaccinated. I take my heterogeneous model here, I vaccinate 70% of the high activity people. Once I vaccinated 70% of the high activity people, it's like my thing is now 1.5, 1.5, 1, 0.5, 0.5. That's a model where we're right at the cusp of herd immunity and the thing will not spread anymore. Yes.
Glenn, just to make sure, R0 bar is not the average of R0. It's the average plus the additional term, which is the variance, depends on the variance, right? It's
correct. Yep. So R0 bar is what you would estimate if you saw this thing starting to take off, and it's how fast you see it growing. And so you see it growing, and so you see it
like
growing.
How an outside observer will compute the R of the population if it were homogeneous.
Exactly. It's how the outside observer would treat the population if the outside observer is just using the homogeneous approximation and saying, oh, this is an R naught equals 2.3 disease. Okay. And that is, but the 2.3 numbers that are in the literature, that's where they come from. They come from treating as homogeneous. So if this model,
once it's not homogeneous, there is no reason that vaccination should be homogeneous. So when you say 56%, that's 56% homogeneous, but you could have different rates in the different groups.
Yes, no, exactly. So in fact, the thing I was going to say here on vaccine targeting, if you have different rates in different groups, the thing you want to do is vaccinate the most active because they're the ones who are spreading the disease.
Oh, I see. I had to pull it here. Sorry, I didn't.
Yes. So, and that's how you can reach herd immunity with 14% vaccinated is by vaccinating exclusively in the high activity group and not at all in the other groups. And doing 14% there actually stops this epidemic. So this epidemic is much more controllable than the homogeneous model makes you believe, and it's controlled with 14% vaccinated, not 56%. Now, homophily, I said, makes it worse, and we think there is homophily. But homophily, it turns out, numerically only makes things a little worse. If you make H.5, 50% in-group and then 50% uniform, you would find that you only need to vaccinate 15.5%. Even if you go all the way to H approximately 1, then you only need to vaccinate 21% of the population. So for H approximately 1, still 21% vaccinations is what's needed, not 56% in this model. So in terms of vaccine targeting, this uniform model. Yes, Michael, you want to break?
So I was wondering, are we going to get into any discussion about the variation or like the correlation between these higher activity individuals and their willingness to get vaccinated, which has been a big topic in this pandemic? Because in the past, you would assume that the high activity would want the vaccine so they could be safe. But now you're seeing a little bit of correlation between wanting to go out and not worrying and not getting vaccinated.
Yeah, no, I agree 100%. In some sense, the model suggests to be 56% vaccinated, or the uniform model suggests 56% vaccinated. The clever targeted vaccination where you vaccinate only the high activity people, 14% vaccinated does it. We have the opposite case of if there's sort of high activity people are the vaccine skeptics, all the vaccines go to these 0.5 people who weren't spreading the disease anyway. We can get much more than 56% and still not have stopped the disease. So if you vaccinate the wrong people, you can go beyond the herd immunity region and not stop it. And it's sometimes like the one comment I had down here is, targeting in the uniform model, you always want to vaccinate the high R0 people. If your vaccine system, like we've had in much of the United States, was based on hassle allocation, it's like you have to sit there at your computer and hit refresh 1,000 times in a row at 3 a.m. to try to get a vaccine appointment at the CVS to get vaccinated, that's exactly the wrong thing to do because, right, you're then vaccinating the people who care a lot about COVID and we're going to be very careful about not spreading it anyway. And that's the exact opposite of what you're going to do. And so this hopeful thing of we only needed 14%, and maybe we need much more than that because we're not vaccinating the right people. This also, I know Michael was talking about some of his stuff on vaccinations yesterday. I don't know if he was talking about, he has this work on should you be sort of reducing doses and giving less effective vaccines to people in order to vaccinate larger numbers. Those calculations, I don't know what he's doing these days, but it's very important that when you're doing that, you should take into account that effectiveness on different people is different. And again, in some sense, we're thinking about vaccine effectiveness as a choice variable. This is another argument for you want highly effective on these R equals 3.5 people, and you really want to target the vaccine source of high activity people, and spreading it out among the other people is maybe not helping when you're going beyond the people. You're going to people who already have low activities where the marginal value of vaccinating them is low.
Can I ask another question about R0?
Yeah.
So the reason we're using R0 and contact interchangeably is like we're implicitly assuming that probability of transmission given contact is the same for all groups.
Yep.
So I'm thinking of long-term homes who had contact with like frontline workers. These have a much greater probability of transmission. So in that case, it would be different.
So the correct way of thinking about the R0s when I'm discussing these models is as the number of disease transmitting interactions you have with someone. So someone in a sort of a skilled nursing facility may have an R0 that's like 30 or something because they over and over and over and over again are coming into close contact with patients. So even if it's only 3 people they see all day, you want to think of them as having a very high R0 because it's the number of transmitting interactions, not the number of interactions. Okay, so some other implications of this heterogeneous world. One other implication is predicting the course of an epidemic is going to be very difficult. Estimating the parameters for a heterogeneous model is hard. The early growth rates let you estimate this R0 bar. How fast is this thing spreading when it's new? What component of that is variance versus mean, however, and that matters to the dynamics later on and matters to the vaccinations. And what some people have done is try to sort of augment this with contact survey data. There's sort of several of these contact survey data. There's like, there's one called Polymob, there's another British one, and where in some sense these contact surveys, they've done sociologists have done large surveys where you ask people, write down in a book everyone that you had a conversation with today or you interacted with today. The difficulty is those contact surveys may not at all reflect the realities of COVID transmission. Like, I filling in the contact survey, I went to a bar with my 3 friends. I write down the names of my 3 friends in the bar. I don't write down the names of the 87 other people who were in the bar sharing a closed space with me. I went to a choir practice. I write down the names of the 2 people I talked to at the choir practice. I don't write down all the people in the room when we were all singing together in a common space. So it's very hard to sort of know what's the sort of variance across the population of activity. Again, you can sort of do this in proportion to cell phone activity, but it's very hard to get a good COVID thing. The parameters of those less active groups are particularly difficult because not so many people in those low activity groups get COVID. Therefore, it's hard to know, are they 0.9 people or are they 0.3 people? How active are the less active? And epidemic paths, it turns out, can depend on the activity levels in these less active groups who are only a small fraction of the COVID cases early on. So I've put a couple illustrations of this out here. The illustration on the left is I made up two different heterogeneous population models. I made up two different heterogeneous population models that have the same R0 bar, but one of them had a bit more activity in the high activity groups and a lot less activity in the low activity groups. One had more activity in the low activity groups. And when you simulate them forward, they take off at the same level, they reach exactly the same height, and then they start turning down at exactly the same time. And yet once they've turned down, one population ends up having twice the number of infections that the other does. Because one turns down and then dies out very quickly. The other has a lot of people who are just slightly subcritical, a lot of people with R0 close to 1. It just sort of, the infection just burns and burns and burns in that population once it's been seeded well. And so whether you're going to be in the red thing or the blue thing, it's just really hard to tell, because you can see what the R0 bar is, you can see what the activity is in the high activity groups, you can't see what the activity is in the medium activity groups, and you don't know whether it's going to burn for a long time or whether it's going to something that's going to end up fairly quickly. The second reason why this occurs is often we have policies where we're temporarily imposing something in order to sort of protect people, and then after we've imposed a temporary policy, we relax the temporary policy because we feel like we've brought the cases back down. What's going to happen with your relaxation? Again, I made up here in red and blue two different heterogeneous populations. These populations behave very, very similar. They behave similar in the uptake. They start off taking off at the left line I put in there. You impose like a partial lockdown. That partial lockdown drives down cases. You have the partial lockdown in place for a while to try to stop overshooting. You release it, and what happens? In one case, you get a new little surge. The other, you get a much, much bigger surge. And this is all, the sort of what happens later in an epidemic depends often on the people who are in the medium activity groups, not the high activity groups that are getting completely burned through. And so it's hard to tell unless you can estimate those parameters that are hard to estimate. Yeah, Sergio?
If there was the second graph, suppose there was a homogeneous population, would it look the same or would it be very different? With a policy change, I mean.
Yeah, so I would have had a homogeneous group would have done something where it went up, and then with that policy, it would shut down and then it would go up again. I couldn't, with the homogeneous group, have gotten it to look so similar to these, I got these two graphs, these are two heterogeneous groups that I made to behave very, very similarly. A homogeneous one, I couldn't have matched the angle of attack and the point at which it turns down and the amount by which it turns down. Right? So in some sense, I was trying to match three different things here: the angle of attack going up, the height at which it turned back down, the amount by which it went turned down before you took the policy off. I couldn't match all three of them with just a single R0. But it would look something like this. Homogeneous model would, again, it would have gone up, gone down, and then peaked up a little bit before it turned down.
I mean, the two bumps, you'll still get them, but you won't get something so dramatic at the 90 days where you had that big.
I wouldn't be able to get something that looked so similar. You would recognize that one of them looked different from the other. When the homogeneous one looked different from those in the short run too. So at least theoretically, an econometrician could tell you, oh no, this is a homogeneous one. It looks like a homogeneous one. Okay.
Can I also ask?
Yes.
Why can't we estimate activity very accurately using cell phone data?
No, so we can estimate activity distributions using cell phone data. What's hard to estimate is the dangerous activity. It's the activity when you have your mask off, or the activity when you're in a bar versus whatever. Now, if you have, I know I've seen some people have the sort of cell phone companies typically don't release the full data. Like if you had a very good data, you could figure out how many cell phones are very close to their cell phone in a place that I know is indoors. Maybe then you could do that. But again, sometimes it's the low activity people, you have fewer data points for them. And so typically people get good estimates from the people who have a lot of pings on their cell phone and less estimates from people who have poor pings on the cell phones. Okay, my view on overshooting is the classic SAR model has all this overshooting. That's where a lot of the dynamics come from. I think it's not so practically relevant. As I said, we're never going to have a world where 13% of people are currently infectious. And so epidemics go more slowly. If epidemics go more slowly, there aren't that many people infected when you hit herd immunity, so the thing dies out fairly quickly once you hit herd immunity. So the overshooting there is not so big. But overshooting again does, so there's a lot of people who think overshooting is not a big deal, which I agree with, but actually I then think overshooting is a big deal because of heterogeneity in models. Overshooting, there's this extra dimension of heterogeneous model, which is a group by group phenomenon. As I said, we only need to have this 14% get infected before we can stop this thing. But if you go in the wrong direction, you can get many, many more people infected and infected needlessly. The infections of any of the less active contribute very little to reaching herd immunity. So if you have this sort of group by group overshooting, you can sometimes think of all of the infections in the lower activity groups are overshooting because they're all more than you need on that closest path to reach the herd immunity range. And then, this argument that overshooting is more important and means that temporary lockdown policies there's a stronger case for. We had a lot of skepticism in the US to lockdown policies, but temporary lockdowns, two additional arguments for them. If you have vaccines coming, you really want to lock down until the vaccines can take effect. If the vaccines are going to take effect quickly, for instance, if you only needed to vaccinate 15%, you could do that much more quickly, and the lockdown would then be more justified. And then also, the uncontrolled epidemics grow in proportion to activity. That is putting cases in the low activity groups. You want things more targeted than that. Temporary lockdowns can keep cases down in those low activity groups and prevent the overshooting. Questions?
I have another question.
Yeah.
So when you're looking at how people, interact and, do they interact more or less throughout the pandemic, and you see, 15% of people are infected today, I'm not going to go out. But even some of these vaccine skeptic people might look and say, well, 40% of the population's vaccinated, I'm going to stop wearing a mask, go out. Do you see any kind of interaction where the vaccine goes up, but because activity goes up, you can see some kind of dampening of those positive effects?
Yes, I think that 100% exists. Let me actually get to that. I'll begin to that topic soon next, or I think. Yes, endogenous interaction. So, okay. So, time path of COVID has just looked very little like the early forecast. So this is there's this early paper by Ferguson that, sometimes this may be the paper that sort of triggered some of the early shutdowns back in March of 2020 when, researchers at Imperial College sort of predicted that here's a simple SIR model calibrated to COVID. It shows that we could get millions and millions of deaths. And this was, considered incredibly, shocking at the time. I think at the time Boris Johnson was happy that like COVID is the flu. I'm just going to let it pass over us, whatever, we're going to be fine. And then these graphs got released saying, look, if you let COVID just spread like SIR, what's going to happen? You're going to get 2.2 million deaths in the United States. You're going to get 510,000 deaths in Great Britain. At the time, 2.2 million deaths was an absolutely shocking number. No one could imagine a million people dying, and so this has sometimes played a big role in getting things to getting things shut down to occur in the United States. But obviously, this is not what the pandemic has looked like. In this early graph, the United States was going to have this massive surge of COVID. 2.2 million people were going to die. They were all going to die before August of 2020. The whole thing was going to come in, wash over the country in the space of 3 months, and then it was going to be completely gone. We lost 2.2 million people, but the whole thing was over. Why didn't this happen? I think this is the thing I've said before. This didn't happen because this could not possibly happen because people wouldn't behave this way. If the death rates are so high that we're getting, what is that at the peak? So it's 17 deaths per 100,000. So that's 50,000 deaths a day in the United States. If 50,000 people a day are dying in the United States, there's going to be so much news coverage of 50,000 people dying. No one is going to be leaving their houses when it's 50,000 people a day are dying of this disease. And so, economists and epidemiologists both recognize this. They develop more enhanced models that capture this in two ways. One is, I'll sort of say, it's a reduced form approach where you just sort of try to empirically estimate behavior. And the other is sort of the rational model, where you try to think about what would be the rational way that people would respond to epidemics if people are afraid of getting sick and dying, and they're afraid, and there's sort of some cost to getting sick. Right? So first, the reduced form approach. Again, this is sort of a classic approach in epidemiology. Again, there's some stuff like this in the 1990s. There's actually more recent. You'd still find people were writing papers in this form. It was an active literature in 2019, pre-pandemic, where people had papers that were just being written about these things. What would be a typical functional form? So here's one I took from the epidemiology paper, the one I cited there, the 2020 paper. You take the R0, SI, I of T infection rates, and then you just put a fraction out in front to say it's going to be dampened by people's endogenous response behavior. And so the endogenous response in this paper is 1 over 1 plus a constant times d dot of t. D dot of t is just the death rate on that date, the change in the total number who died. So this is people respond to deaths. And so you just take 1 over 1 plus a constant times the death rate, and then you raise it to the kth power, just give an extra parameter you can calibrate. Either it's linear or it's sort of, very steeply increasing, or it's very steeply decreasing, but you just have a flexible functional form with these sort of two parameters, A and K, for people respond to death rates and cut back on their activity. Okay. And there have been a few papers calibrating. So the Whites et al. Paper is a paper written by epidemiologists, published in PNAS. The paper by Andy Atkinson is a Minneapolis Fed working paper, Atkinson and co-authors. Many people have calibrated these and say that calibrations very strongly support that there is some kind of endogenous distancing of these kinds. The first order fact behind this is, here's a graph I took from the Atkinson paper of what was the daily growth rate in death rates. And so, what's the sort of growth rate of number of people dying per day? This is something that should decline in an SIR model because, the growth rate there is the R0 times S or whatever. But the R0 times S only declines when S declines. S doesn't decline very rapidly. Even early in academic, we're getting 1%, 2%, 3%, 4% have been infected. It's moving from 1 to 0.99 to 0.98. These things ought to decline very slowly. What you see instead is that they decline very rapidly. The daily growth rate was like 10%, 10% on the first few days of the epidemic. And then it goes from 10% down to roughly 0, 40 or 50 days into the epidemic. And then from there, first, we're used to sort of seeing these things and say, oh, there were waves and things went up and things went down. But first order fact is that they were roughly constant for months and months and months and months and months. And so, infections really seem to stabilize. And so it's not that they sort of slowly declined as S increases. Instead, they went very fast down within sort of, say, a month, and then they stayed very flat thereafter, even as more people were getting infected, therefore more people no longer contagious.
Doesn't this suggest that you should look at dt rather than d dot t? That what matters is actually the death rate, not the change? Or I got it wrong?
I may have said it wrong. I have it right on the slides, I think. So yeah.
No. I'm talking about the slide. But what affects people's behavior is the change in the death rate rather than the
D dot.
death rate itself?
D is being used here for the total number of people who have died. And so D dot is the number of people dying on date T.
So
And
that's a change. That's D dot is a change from one day to another in how many people are dying.
No, D dot is number of people who have died totally. So D dot is number
Oh,
of
so
who
D
died.
dot. Oh, I see. So D dot is it's in fact the number of people that died on day T.
On day T, correct.
I see. Okay, that's what I thought is the right amount, not the change.
Yeah,
Okay.
and the empirical literature says that does seem to be what people rely on, is the number of people dying today. It's on the news. That's what people react.
Okay. No, that now it fits. Okay, I just misunderstood what D means.
So, a reduced form model like the one I've showed you here, so you fit the parameters A and K and say, can that describe the data? And the basic answer is yes. That is, you put in the proper A and the proper value of K, you can very easily account for the fact that these things, the infections peak at like 1% infectious, not 10% infectious, and that declines have been, very slow. People also describe it as plateau-like. Cases go up and then they start to come down, but then basically they plateau and run across for a very long time. What you just need is those A and K parameters to keep the steady state, to keep the sort of what people call the RT, which would be the R naught divided by 1 plus A D dot to the kth power, very close to 1. And as long as you sort of, and given that the number of people dying per day has been fairly constant, it's not hard to sort of keep if the number of people dying is fairly constant, it's not hard to keep that sort of, denominator equal to 2.3. As long as that denominator is equal to 2.3, just like R naught is 2.3, you divide by the 1 plus 2.3, and you're going to get 1, and that's sort of what happens. Now, there are some features that don't fit the data as well. Mobility data suggests that activity increased even before the peak. So it wasn't that it wasn't that we had this peak in deaths in the US, and then after the peak went down, people started leaving their homes. People actually started leaving their homes, going back to be more active during the peak and even a few weeks before the peak. So the one thing that suggests is that there's been some pandemic fatigue, and that this model is not the correct model, because what people often have is that there's some sort of increasing disutility of staying at home, such that the longer you've been quarantined, the more you're going to go out, even if the deaths are higher. And so what we probably need in this thing is not just the deaths today, but we also need some function of previous social distancing activity, where previous social distancing activity has a negative impact on the social distancing I'm going to carry out today with the data. Okay. The other thing we've seen is, while R naught has stayed close to 1, it has peaked several times. There are models that generate those cycles entirely within a model like I've given you before, because there's this gap between when people die and when they get infected. Those gaps can be on the order of about a month. So the death, the peak infection death date is about a month after the peak infection date. But you can cause cycles in that, where people, every time the deaths get high, they become safe, the deaths go low, and then they sort of see the deaths go down and they go back out. But actually, I think what's going on in the data is not that, but there's seasonal effects of COVID, and there's these variant-driven changes in transmissibility. And we have now the 4 named alpha, beta, gamma, delta variants, but there are many more variants than that. There have been variants in New York and variants in California and variants in many places. And I think many of these cycles where the R naught gets bigger than 1, RT gets bigger than 1, are variant-driven cycles, where sort of a new variant comes in, the new variant makes things more contagious. Behavior hasn't adjusted in the short run. We see things go up, and then it's only as things have gone up and then deaths start to get noticed that we then come back down. Rationality. Can economists actually sort of explain this all with fully rational models? So if you think about it, let's imagine just the simplest model I could write down, which is myopic endogenous response. Just every day, I don't do a dynamic programming calculation and just sort of say, should I leave my house today? Should I not? And all I consider is the probability that I will get sick today, not thinking about the future probabilities I'll get sick a month from now and how I need to discount that. Well, in that simple 2x2 game model, it's clear that if I is low, nobody's going to socially distance. Everyone will just go out and go to the market. If I is very high, then you have a strict best response not to go to market. And therefore, for intermediate levels of people going to market, agents are going to mix. The mixing has to keep you indifferent between going out and not going out. But then in order for the mixing to keep you indifferent between going out and not going out, I has to be exactly at that intermediate point where you are indifferent between going out and not going out. And so that suggests that with rational agents, there would be rational myopic agents, there would be some fixed I, and we would just see a fixed infection rate that balances out when people are willing to go out and not go out. Okay. You can then make a much fancier model, and you can do a dynamic programming thing where people take into account the sort of net present value of the future likelihood of getting sick and when they're going to get sick. Some models like that, people have written papers showing that, oh, these things can have multiple equilibrium. There can be equilibrium where everyone goes out because there's nothing you can do, and we all get sick, and there's another equilibrium where we don't all get sick. But in general, what's kind of that model is, and like there's this paper from Poxberg that I have on my references. Basically, that intuition from the myopic model can still hold in a dynamic model. So in this graph, what I've graphed in the blue line there, the dotted line is how this thing would proceed as an SIR epidemic. The blue solid line is how it proceeds with the endogenous behavior, and the red line is the endogenous behavior. How much do people, what fraction of the time do people go out? And what you see is that early in the epidemic, everyone goes out, infections are low, and the epidemic just proceeds. When the fraction infections hit some threshold where people are now indifferent between going out and not going out given the risk of infection, lots of people distance. The infection rate flattens out. And in fact, the equilibrium of this model is it goes up, it hits a plateau, it flattens out for many, many, many months. And then finally, once the infection rate has been widespread enough people are no longer susceptible, then we're in the herd immunity region, things start to decline out, even though people are going on 100% activity. But so what this says is an endogenous model. What we see is not the SIR, bell-shaped curve of infections. What we see is a rise, long flat period, and then a fall once we've reached herd immunity with very little overshooting going on. This endogenous social distancing is a good thing. It improves social welfare relative to SIR by sort of reducing the amount of overshooting that we get. Social distancing in these models, though, is not going to be optimal because everyone exerts a negative externality on others when they're infected. Therefore, social planner would do more distancing than people do endogenously. The social planner would start distancing earlier. The social distancer planner would also sort of keep cases lower during the plateau so that we have less overshooting than we have at the end of the plateau in this case. And I would say that, yeah, go ahead. Question?
Sorry, I'm guessing that people who are very active, some of them are very active because they don't have a choice, because that's their job or something like that. And I was wondering how this affects this result. The plateau.
Yeah, this model would be okay if you added a little bit of heterogeneity in that sense. You can sometimes use this as purifying the equilibrium. And so in this equilibrium, what you're seeing is that even in the peak of the epidemic, the epidemic doesn't peak very high. And so when it peaks, people are mixing 70-30, 70% stay home, 30% go out. So you could purify that and have 30% of the people going out and 70% of the people staying home, as long as the sort of fraction who had to go out was less than the 30% in this model. And obviously for other parameters that will change. It may be sometimes the thing jumps to 80 or 90% staying home, and it's harder to do that. But it's the thing is rising when everyone is willing to go out, and so then once it hits that threshold, it's still only some of the people who are staying. It's always mixing, because otherwise you would want to go out. So.
Glenn, sorry, the reason that after the plateau it goes down is that you have reached S bar by then?
We've reached
Why does
S bar. Yeah, at the end of the plateau, we've reached S bar. So
S bar has been reached, I see. So essentially you have reached S bar later and you have flattened it, and that's the point where you can relax everything, right?
Yeah.
I see. Okay. But that was quite quick. Okay. That means S bar in this example is not very high. Somehow it seems like I don't know what
Yeah, I guess
don't
I don't
know
know if the
what
scale.
units are there, but somehow
Okay.
it's
No, but I
it's
would
a
assume
very
this part,
optimistic
like
kind of scenario.
this scenario was based, like, this one was this paper. The paper that does is sort of calibrated the 2.3 number, so it's probably the S bar is 56%. So this is probably showing you a graph where it's like 50. The area under the blue curve to the left of that point probably is the 56% or so.
I see. Okay. So it was tailored to get, yeah, okay.
Yeah, but I would say that, like, I think accounting for effects of endogenous distancing is really, like, many papers don't do endogenous distancing, and I would say, if you're thinking about policy analysis of requiring people to wear masks or getting people vaccinated, the endogenous distancing is potentially very important, because if you're getting in this mixing region where you're going to have people mixing, whatever you're doing to sort of make some people more safe, if the other people just adjust to keep that sort of infection rate right at that sort of threshold plateau level, your policies could often have just absolutely no effect. Because if your policies just keep everybody mixing, but have people mix, even if you make a bunch of people safer, you've done something, but you've got people mixing, you may still have the same infection rate while you're plateaued. And so that's something to think about. Okay, final graph. No, go ahead.
What's plateauing, or it's the new cases, right?
The new cases is plateauing. Yep.
So does that mean that when if we plot the number of the fractional susceptibles, we're going to have like sort of a linear segment which then flattens?
That's right. So if you plot the fraction susceptible, it would sort of, it's going down. Fraction susceptible is going down slowly, and then has a long linear segment where it goes down at a linear rate, and then it again then it finally slows once we get past the herd immunity region, and then it heads to it goes to whatever its asymptote is. Yeah.
But doesn't that kind of have like that saying that, because like if we consider the reproduction number as R times S of T, then that's saying that we're going to have a constantly decreasing effective reproduction number.
Yeah, I think that's what it seems. It seems like it seems like what's going on is it's the R times S of T divided by 1 plus alpha times D dot. And so what's happening is as the what's got to be happening is the behavior as the susceptible is changing. Oh, this is working. Yeah, it's got to be but the behavior is going to be checking the death rate. So yeah, I guess I'm getting myself confused trying to think about how that's working, but it's the
like I mean ignoring the deaths altogether. If we have if we're thinking like, because if R is really high but we have no susceptibles, then the R is not really an important number anymore. So what really matters is R times the number of susceptibles. So we kind of already have an endogenous
but
number there.
What's going on here though is that so I think I'm getting myself straight now. So what's going on here is that you have the number of susceptible is going down, but then the people who are susceptible are going out with a higher frequency. So the people who are susceptible are having more and more interactions in order to keep the death rate constant. Because in equilibrium, we've got to keep that death rate constant, keep the infection rate constant, because that's sort of, otherwise everyone would be staying home or everyone would be going out. And so what happens is the sort of equilibrium is among the people mixing, more and more of them are going out in order to keep that thing I captive at its equilibrium level.
Oh, that's the indifference part, right?
Yeah, that's the indifference part. Okay, so final thing I had to say is, so it's again, even in a period like in the US when we've been sort of vaccinating a ton of people, R has stayed remarkably close to 1. R was sort of hanging out remarkably close to 1 for almost a year. Now with people vaccinated, R has gone below 1, but it's gone below 1 to like 0.93 or something like that. And it's sort of, we're still seeing this sort of very, very long arc close to 1. And you think about, like, how does this happen in a heterogeneous SIR model? You know, in a heterogeneous SIR model, R being approximately 1 is this sum, R naught I, your activity rating group I, times susceptibility times R naught I minus 1 has to be about 0. We have a lot of people who are now vaccinated, but you just, groups with R naught that are very low can't contribute much to this sum. So like any positives in this sum have to be offset by negatives in this sum. If your R naught is low, you can't be contributing very much negative to this sum, right? Before we even had vaccines, you can't be lower than negative 0.25 because, you know, R naught times R naught minus 1, you know, the minimum of that is negative 0.25 if R naught is 0.5. So before vaccines, you really couldn't get much in the way of negative terms from any group. Therefore, even the groups where we think of as skeptics, we think of as irrationals, those irrational groups still have the endogenous model had been working pretty well for them because the low activity people can't really offset the high activity people by very much because they're not very active. So what we must have been seeing was even the high activity groups, R was close to 1. Now with vaccines, this expression, when if you make R is high but S is 0, then this thing can get negative. But what this is telling us is that even those groups that are highly active and vaccinated, it must be they're being offset by other people who are high, other people with R naughts greater than 1, who are sometimes picking up the slack to keep this thing from going down, because this thing ought to go down a lot when you have active people getting vaccinated, and it's not going down very much. And so in some sense, endogeneity seems to be just a very powerful force. I think that's the lesson I would take from this. Any questions? Okay, so if that's it, I'm basically coming to my time. I put 2 pages in my slides with lots of references for those of you who are interested in learning more about this. So I have a overview paper that I have in the Journal of Economic Perspectives on heterogeneous SIR models. I put in a couple of the classics of mathematical biology in the 1990s. I have a working paper bringing out some of the current implications in COVID economics. If you want to see sort of samples of the macroeconomic papers that talk about COVID mitigation policies, how do we mitigate removing damages? I put some references to papers that do those kinds of things there. Endogenous distancing, there's some papers that do this in reduced form things. The White's paper is sort of biologists doing this. Atkinson is economists doing this. Funk paper is actually a very nice survey of endogenous distancing from the mathematical biology perspective from a decade ago. So the endogeneity is not something that only economists have thought of. But then the recent rational distancing models, I put some references there. And then finally, some empirics on endogenous versus policy-driven distancing. The Chernozhukov paper makes an argument that no policies really mattered, especially mask requirements. Goolsbee-Syverson paper argues that most of what we saw after policies were implemented was not the policy effects themselves, but just the endogenous distancing that people did on their own, not necessarily causally related to the policies. Okay, and so that's all I've got unless there are questions.
Thank you very much, Glenn. Any further questions? We have some time.
I have a question.
Yeah, please go ahead.
I have a question regarding the variance, like we mentioned earlier. So throughout, we've been using R naught as kind of like, it encapsulates the contact rate and probability of transmission into kind of like one metric. But then usually, sometimes you see like the beta being used, like the contact rate times the probability of transmission. Now, is it possible to basically tweak this second model to incorporate different variants by changing the probability of transmission part, but keeping the contact rates the same? So is that now possible to do with the one metric R in place?
Yeah, I guess yeah, so the way I generally, my starting point typically for thinking about variance is like I would almost, you can, one way to think about it is you can start by some sense just modeling each epidemic separately. So there's an alpha epidemic going on, there's a delta epidemic going on. Think about the delta epidemic as being, we have this sort of new disease that's very small, but it comes with a fairly high susceptible fraction because, maybe, like I saw data in Israel that said half the people with Delta are already vaccinated. And if 80% of adults are vaccinated, that would maybe say the vaccine gives us 75% protection against it. So sometimes you sort of think of Delta as being a new epidemic that's just starting with an S of 0 of 0.6 or 0.4 or whatever it is, instead of starting with an S of 0. And then just think of it as evolving given that different S naught, so it's got an R naught, but it just comes into a world with a big S, and that's where we're going from. Obviously, if you have countries that have multiple things that are going on simultaneously, like there's an alpha epidemic and a delta epidemic, I guess England is mostly delta by now, but like in US, it would be 25% delta and 75% other stuff. Obviously, you have these sort of two differential equations going on simultaneously, and each one, susceptibility according to either one, is feeding into, since there's cross immunity, you would have to do that. But I think for that, you'd have to, I haven't really seen people do good models of that. You really have to have these two parallel differential equations going on, each one feeding across. Because it is, they're going to nap, I think normally one goes faster than the other and basically takes over. And then we just, again, are back to the sort of one disease model works pretty well.
That makes sense. Thanks.
Yeah, and there are models like I did these heterogeneous models with heterogeneity and activity rates. There actually are models with heterogeneity and transmission rates. And I think like for thinking about adults and children, that may be something you want to think of, is that children may be less likely to transmit the disease. And so there are also versions of these models worked out where the heterogeneity is in the transmission rate rather than the activity rate, but it's fairly similar because I'm just multiplying Ri times Rj, and so the math is almost the same if you do that.
Thank you.
Any other questions?
I have one.
Go ahead.
So I'm trying to think about the endogenous distancing in the Israeli case. I have a feeling that we didn't have a plateau, and that maybe it's because not enough people died because we had a very effective early lockdown. So do you have a sense of, like, empirically, when does the endogenous distancing kick in?
Yeah, because I know that I've seen that, there's there's papers on the US showing that this R equals 1 approximation seems to work pretty well. And there are other, Japan seems to have had this R equals 1 for a year or whatever. And then I know there's some countries where India was a very slow decline from their first thing, but then a very fast spike in their second case. And there are other countries that have had these very fast spikes up and down. And so, yeah, I don't know. In some sense, the papers that do the endogenous distancing models are always writing about the countries where the model fits well, not the ones where it doesn't fit well. And so I don't know what is it about some countries that may not have had enough endogenous distancing to stop the pace of the, clearly the Indian case, that second wave where it took off so fast that, and was apparently so contagious, it was very hard for people to get out of it.
Okay, thanks.
Glenn, thank you very much.
Okay, thank you very much for having me.